We're now going to talk about one of the great mysteries of centrifugal pumping, and that's NPSH and cavitation. That's a very much misunderstood subject amongst pump people, and I'd like to take you back to the basics that underpin it all. So NPSH and cavitation is the topic that we're dealing with, and we've got to understand what NPSH stands for. It stands for net positive suction head, and that is basically the pressure that is applied at the pump suction. Net positive suction head. The NPSH actually consists of two components, and there is NPSH available, which is the pressure that belongs to the system. In other words, the suction system that feeds the pump with fluid. It's a function of the system design, and it includes losses in friction and so on, and a static component. NPSHR is a phenomenon that belongs to the pump, and this information is given to you by the pump manufacturer on the pump performance curve. So it's a function of the pump, and it is determined by testing for NPSH in the pump manufacturer's works. It gives us the value of pressure that has to be applied at the pump suction to prevent cavitation occurring in the pump suction. Okay, for successful operation of your pump, the NPSH-A must be greater than the NPSH-R of the pump. For water, it's at least 1 metre. So that's the industry you guys are basically working in. So net positive suction head is a method of defining pump suction conditions, and it allows us to predict whether cavitation is likely to occur or not. NPSH is usually expressed in metres, so we have to look at the units of measure for the various phenomena. NPSH-A, I told you that belongs to the system. And it is the difference between the pressure at the suction eye of the pump and the vapour pressure of that fluid at that flow rate and at that temperature. So all of that is determined by the measurement of NPSH-A. You have to calculate the system head on the suction side of the pump and then take away the vapour pressure that's required to keep the liquid as a liquid. And you can get that data, HV, it comes from tables. And you can get it for water, and you can get it for other common liquids that are pumped. So HS is the absolute suction head of the pump suction. HV is the vapour pressure of the liquid being pumped at the pumping temperature. And here are the calculations. I'm not going to take you through that, but that's basically the way you calculate HS, and that's the way you calculate HV. But most of the time, you're going to read that from tables. I gave you the information some time ago about the PIA handbooks, and all that data is in the friction handbook. NPSH-A should be greater than NPSH-R, otherwise you risk the incidence of cavitation. So let's take some typical suction conditions, and that gives us a bit of an idea of whether cavitation is more likely on suction head or suction lift. You can see that this diagram we've seen before in other units. This is with suction head. So the surface of our liquid is above the centre line of the pump suction. And we've got atmospheric pressure pushing on the top of that liquid. So the pressure here is atmospheric pressure plus the positive head of 3.5 metres less the friction head of 1.5 metres. And if we look at our atmospheric pressure at a particular temperature, we've got a temperature of 15 degrees C, atmospheric pressure will be 12.35 metres. We would normally measure it in bar or millimeters of mercury, but for our purposes, for NPSH, we need to have it in meters. So that's the conversion calculation to give us NPSHA. The vapor pressure, again, we're going to get from tables, but it's either 1.7 kPa or 0.17 meters. And we want the 0.17 meters because that's the measurement for NPSH. This is a suction lift situation, and here you can see the situation is quite different. We're starting off in this case with a water of 26 degrees, and we're going to go through the same process. This time we've got atmospheric pressure pushing on our water surface, but we've got 2.2 meters of suction lift that's working against us, and we've got pipe friction of 2.15, which is working against us. And if we go through the calculation, we can see that in this situation, we had an NPSH of 12.18, and in this situation, we've got an NPSHA of 5.69. We have to compare those figures with the NPSHR shown on our pump curve. So we would normally look at the worst case scenario because we're never sure exactly where the pump is going to be operating along the curve. So if we see that the worst case NPSHR is 6 meters, we'd be in trouble with that pump if it was on suction lift. But if we go back to the suction head, then an NPSHR of 6 meters is easily accommodated. So the difficulty comes when we're in suction lift situations, or more importantly, when we've got high temperatures of liquid that we're pumping. So this is particularly important in boiler feed situations in a power station, because a boiler feed situation, we've got high temperature water and we're trying to pump that, and we've got to have a great deal of pressure on the suction side of the pump to prevent cavitation. The figures that I've given you are all based at sea level, where atmospheric pressure you can calculate based on the information that you're given. If you go up Mount Kosciuszko or Mount Everest, the pressure that you will read will be different. So atmospheric pressure will be lower in that situation, and water will boil at a lower temperature. Let's say, for example, up Mount Everest, it might boil at 85 degrees C instead of 100 degrees C. And with other equipment, for example, with diesel engines, they derate the engine if it's going to be operating at high level because the atmospheric pressure is different. So these are sorts of things that you just get used to in the industry. And if you know that it's going to work at high altitude, then you adjust accordingly. And you work out what your atmospheric pressure is based on your barometric readings. The negative pressure at the gauge depends on how much friction loss there is, because you've got a positive head above the pump center line, and that might be 1 meter. But if you've got 3 meters of losses in the pipework, that may be the killer. And I can't tell you what all those losses might be until you do the calculation. But it's not a complicated calculation. So it's worthwhile sitting down with a calculator and a measuring stick and some friction tables and just doing it on site. And then you've got something concrete to discuss with your client. Don't work on the basis of what it might be, work on the basis of what it is. And you can only do that by measuring things. I'm a great believer in measuring things. There's an old saying, if you can't measure it, you can't manage it. And I believe in that. If you know how much money's in your pocket, you take it out. I've got $5.50. Can I buy a coffee? Yes, I can, because I know a coffee costs me $5.50. That's the sort of thing. I can manage the situation because I've measured the parameter.